S32 on the mixer. Bottle of water or something. Okay, folks, I'm going to start in a minute. I've got myself sorted out. Sorry, I was just getting a little bit of code sorted out for the lecture because today there's a few examples. I feel I had them all straight before starting to talk. Just make sure the textures are reasonably sized. Good. I feel like I can hear myself. I'm speaking. The music is probably loud right now. It's still quieter than me, so that's good. I'm going to start recording. G'day, folks. Welcome to week 11. We are here, week 11. I'm just checking my meters, my sound level on the meters right now, and it seems to be okay. I'm not peaking too badly. I guess if I get really excited, it might peak slightly. I'll give it a little touch more gain. 1 more dB, please. It's hard to get gain right, because if you peak, it's really bad. You don't want to peak. And I should have a compressor or something, but anyway, here we are, week 11, COMP1720/6720. We are getting serious now. It is the end of the semester, and I know that some folks are starting to feel a little bit edgy about what's happening over the next few weeks. Why would it be edgy? Well, at the end of the semester, you have many due dates. You have due dates for second assignments for your courses or final assignments. You've got major projects that come due. You've probably got some exams that you're worried about over the weeks after the end of week 12. And it's a lot. The reality is that the end of the semester is always very stressful. The end of the second semester here in the Australian course calendar is usually a little bit more stressful than the end of the first semester because you've got some slightly more advanced subjects this semester, a few more major projects that tend to run over the calendar year. It's just a little bit more than the end of the first semester. So if there are folks out there feeling like, this is terrible, I just can't handle this, I hear you, I understand you. Your pain is shared. We've all been through this experience. The reason you are feeling stressed is because you care about your work. And that's a good feeling. It means that you are an actual human being. So that's good. Obviously, stress is unpleasant. But sometimes we put ourselves into difficult situations in our classes. We put ourselves into difficult situations. We do university degrees. No one is forcing anyone to be here to do a university degree. This is a choice that you're making about your life, about how to, what you want to do, how you want to spend your energy to learn things, to get better, and challenge yourself. And it wouldn't be important if it wasn't challenging. Everything in life which is important is a challenge. So I know that you're feeling stressed. I know that it's unpleasant, but this is why you're here at university. You're here to challenge yourself. And these times at the end of the semester are really, really challenging. They're where things start to get real in terms of the amount of marks that assessments are due. These are the assessments, of course, that tend to determine the outcome of your final mark in a course. And I know that everyone wants to do as well as possible in courses. Of course we do. But the only way to do that is to put in the hard work for these assessments. There's no way out but through, folks. We can't make life so that you get an infinite amount of time for every important assessment task. There are hundreds of students in this class and in every other class, and all of the assessments are kind of around the same period. So moving assessments around doesn't really work given the number of students and the very broad range of assessment tasks they have in other subjects. We set the assessment for the major project to be due after the end of week 12, but before the exam period on purpose, so that it's after the hustle and bustle of the semester, but it's before people have some huge, scary exams that they're probably studying for. So that gives folks a decent number of weeks in this course. You've got weeks from week 9, 10, 11, 12, about 4 weeks of time to prepare for the major project. Of course, I know people do a lot of work in the last few days, and you might have other assessments. The answer to that is not to delay assessments, but to do more work now. So my advice today, which I'll give you on the next few slides, is to acknowledge that the end of the semester is a stressful and difficult time. We all acknowledge that. To acknowledge that this is the challenge that you're signing up for at university. We all acknowledge that. To acknowledge that the challenge is worth it. It's worth it to push yourself. You really learn when you're pushing yourself, when you're trying really hard to do as well as possible. That's when you really learn, when you really get better as a person, really. So it's worth it to do that. And that the only solution is to get through it. The good news, as one of my Year 12 teachers in the last year of high school told me, was when you've got very, very stressful times, such as the end of a term, the end of a semester, a week when there's just seem to be many assessments due, you can be sure that time will roll on and it will pass. It's just a moment in time that you have to deal with. It's sure stressful when it's happening, but at a time continues to proceed at a rate of 1 day per day, and it will be done in a few weeks. So keep things going, keep yourself together, make sure you get sleep, prepare for your assessments early, get things in, keep working, try not to freak out. It will be done, and you will see the results. It will be worth it. That's my pep talk for dealing with the end of the semester. Yeah, folks, I'm just making sure I've got the chat open. There it is. I've got the chat. Yeah, I say this because there was a post. There was a post in the forum today, or a few days ago. I think it was on Friday, from someone who said, well, I've got a lot of assessments due at the end of the semester. Well, yeah, of course you have a lot of assessments due at the end of the semester. It's the end of the semester. That's when all of your work is getting assessed. We're looking at everything you've done over your weeks of learning in your course. And part of the learning in this course is doing your major project is your learning. So we're spending 4 weeks doing this project, not 2 days at the end, not 3 days at the end, not a weekend at the end. 4 weeks spending doing the major project, and the lectures and labs are here to support your major project, not to distract you from it. So let's get stuck into this lecture. Simulations, Dynamics, and Artificial Life. This is the third of 4 topics related to kind of extensions from this course, some recent developments, looking at other kinds of artworks, and looking at topics that are interesting to P5 without being a core part of the course. They're here either because they could be supporting your knowledge for the major project, giving you some more touch points to look at, some examples that you might feel like you want to incorporate into your project if you want to, or just to pad out your knowledge of art and interaction computing with some important and interesting topics. So they're either for your interest or something you want to put into your project, or some supporting information that will help you frame how your project reflects recent developments in art and interaction computing. So, a few positive affirmations for the day. Positive affirmation 1. I have started my major project. Everyone repeat with me. I have started my major project. I have committed my recent work to GitLab. I have been adding to my SOO as I go. I have been adding to my SOO. I have looked at my major project at the test URL and I have verified that it works and it exists. When I need help, I have asked on the forum. The positive affirmations. Don't you feel better saying those positive affirmations with me? Feel free to say them aloud at home. If you're out in Canberra or in a library somewhere, feel free to say them out loud, and the other students around you will also benefit from your positive affirmations about your major project, about the end of the semester. Just making a start on your major project will help you start to feel better about the work that you've got to do. Of course, it's a big project. It's not an immense project. It's not an impossible project. Everyone can do this. You've done your assignments. What you have to do now to complete this course is to do a slightly bigger assignment, but not a hugely bigger assignment, which is the major project. Whoops, well, that's an old slide. I think I deleted that one. Major projects, getting help. Getting help with your major projects. You've still got a chance for getting help in your major project. There's 2 labs left. the week 11 lab this week and the week 12 lab. So this means that you have the chance to share any problems, solutions, ideas in your labs with your tutors, get some help, and also talk about it in the course forum. We do love to see questions and discussions. I even loved getting the question about the due date for the major project, because it let me talk with someone who had worries and concerns about their work. And I know there are folks out there with similar worries and concerns, and it was great that someone asked the question so that we could talk about it. On the forum, there's nothing wrong with showing off your MP if you're comfortable. You've got the test URL to let people see your MP. So if you want to share it, ask a question of other people, ask a question of the tutors on the forum, feel free to post anything you want on the forum about your major project. It's an open kind of culture we build in this course, an open culture of sharing, not a culture where you should be protecting your major project as a secret until it's marked, because everyone is aware of our policies about using other people's work. Everyone is aware of how to cite other people's work, and there's a huge amount of material available to support people. So it's not really a situation where you should be scared to share your work here and seek other opinions. I've got a few tips here about major projects. A few tips. Tip number 1 is sketch. We talked about sketching a lot in the last few weeks, and it's still not too late to be sketching. I've been teaching you about sketching in code for this whole course, 11 weeks. It's not too late to try different ideas about your major project and sketch different angles. Make a little scene. Just start a new file on the P5 editor. Try something out. The more you sketch, the more you find good ideas. The only rule is work. That's how art works. So by sketching, you create a lot of ideas that you can use. You create a lot of ideas that you might not want to use, but all of the sketching is worth it. It all helps you to refine your skills with P5. It helps you to refine your artistic thinking about this project. User testing. This is a bit of an HCI vibe here with this one. Usability testing. Send one of your friends your test URL and watch them physically. Hopefully they've got their laptop there. They open up your artwork and watch them use it. Don't tell them anything about it. Just watch them and see what they do. What do they do first? Where do they get stuck? How do they try to use your artwork? Even if it's not finished yet, this is a useful thing to do. Just to see how someone who's not you would open up your artwork. Because when your artwork is complete and sent in, it will be looked at by people who aren't you. And of course, it's important to make things that satisfy you, but it's also important to understand a little about how other people might see it. And the best way to do that is to show it to them and to let them try it without telling them anything about it. That's how I will be marking your work. I open up your artwork and I just have a look. And then after that, I read the instructions. So the first thing I do is open it up. Think about what the wow factor is in your major project. What is it that makes your project stand out? So when I open your project up for marking, or someone views it in our online gallery at the end of the semester, what is going to make someone think, oh, that's a cool project, or wow, that's interesting? Hopefully the thing that people like about your project or make them go wow or get them interested is the same thing that you want them to be interested in. So you need to make sure that your sketch is presenting itself in a good way, or your artwork is presenting itself in the way that you want, and you haven't added something that distracts people from your main idea. So your main idea, your articulation of the theme, all of your in rewarding interactions need to be aligned with what people are interested in. Maybe your project doesn't make someone go wow, but it could still have a really interesting part, the thing that grabs their attention, the hook. There's lots of ways to frame that same idea. Writing your statement of originality as you go. Remember that everyone has to have at least 2 references in their statement of originality in this course. That's because I want everyone to understand that statement of originality is something that's important to your work to help support placing your work in context, in a scholarly context, in an artistic context, and in a technical context. You need to start it now as you're going, adding things to your statement of originality. If you don't add something to your statement of originality, you are guaranteed to end up in an academic misconduct situation. If you add a picture to your sketch, if you add code from the internet, and you don't have it in your statement of originality, we will be having an academic integrity investigation meeting to discuss it. The best case scenario is that you don't get your mark at the end of the semester when you expect, and it's delayed by a while. So no one wants their marks to be delayed, but I can't help it because of the timeline for doing academic integrity investigations. It takes at least 2 weeks to do an investigation, minimum, and probably 3 really. So because of the ANU policies for it, that means that you miss the deadline for marks getting handed in. So if you want to make sure that you get your marks on time, you need to make sure that you're not in an academic integrity investigation, which means that you need your statement of originality to be perfect, to be absolutely fully compliant with our requirements. You need to make sure you cite every file and asset you used, any bits of code that you've borrowed, any ideas that you're borrowing from other people need to be in that SOO. Push to GitLab all the time. All the time be pushing, always be pushing. You know how to push to GitLab because you've done all of your assignments already. So it's mainly a matter of habit, getting into the habit. We will be messaging people who haven't pushed to GitLab enough this week to make sure you start. It's not a situation where you want to be doing all of your work at the last minute. So if you're not pushing already, you're not really doing your major project in the way that we have taught you to do it. So integrating the learning of this course means starting now and pushing now. A few rookie mistakes. You don't want to be like these kids, rookies at soccer. They make mistakes all the time because they're kids, but we don't want to make mistakes. You've done a lot of training this semester in artworks, art and interaction computing, and we don't want to make rookie mistakes now. First mistake, not reading the spec. Folks, you need to read and reread and reread again the major project page. Make sure you are doing a major project for this course. You're not doing a different assignment that you've invented in your head because you think something's a cool idea or because you saw your friend doing something different and you thought that would be what the project is about. Make sure you actually read the assignment page and follow the spec, follow the instructions. Making a game. We've talked about this a lot. Don't accidentally make a game in this course. If you want to make games, we run a course in game development starting next year. Go do that course. It'll be great. Games are amazing. I love games, but they're not the same as artworks, and they don't always communicate a theme in the same way, and they don't make sense on the wall in a gallery in the context in which we provide the major project assessment. So the major project assessment says your work, you have to imagine that your work is going to go on the wall in a gallery, people are walking past it and they might interact with it. If you make a game, it assumes that someone has decided to interact with it for a set amount of time until they get to the end of the game, which is not how this assessment works. You can't make that assumption about an interactive artwork. So we've talked about games a lot. There's a page on the website about how games and artworks are different and how they're both great, but we really focus on artworks here, not games. If you want to incorporate some game-like elements, that's something you need to be very careful about, because you can start to accidentally make a game if you start doing things like a score or a narrative or characters. Having games can be, first of all, something which is much harder to make than I would expect for a major project, and secondly, they make it difficult to have the same kind of interactive experience that we would expect with an artwork. Final rookie mistake, not testing not the final one, second to final, not testing of the test URL. Folks, a few of you have come unstuck in assignment 3 about not testing of the test URL, and we've been reaching out to folks to try to get their assignments working so that we can mark them properly. For the major project, we will not be doing that. If your assignment doesn't work at the test URL, that will be on you in the major project, and you can expect to have a pretty heavy penalty of marks if your assignment is not completely working. If it's not working at the test URL, that suggests that either you've got assets in your code in the wrong place and they're not getting picked up, or they haven't been added to GitLab at all. So the test URL is provided to you as a service to make sure that you can test your assignment the way that we will see it. You need to test it regularly and probably at least a day before the due date for the assignment, because on the due date for the assignment, everyone is submitting their work at the same time, and it can take a while for your assignment to go through the CI pipeline. So you might not be able to test it at the test URL in the last 2 hours or so before the major project is due. So you need to have done that already. People always are on the forum, oh no, it's due in 5 minutes and my CI job hasn't finished. I don't know if it's right or not. It's like, well, too late now, right? Too late now. You need to make sure you've tested it well in advance so that we can see it at the test URL, so that you can verify that it's right. Because if the assessment deadline goes by and it's not right, it could be bad, right? I can't guarantee that it'll be bad, but it could be not what you want. So make sure you're tested early, tested often, and use that test URL to show other people your work and make sure everything is working that way, and you'll be fine. Putting an example in the microwave. I don't see this so much these days. I think we've changed our assessments a little bit, but it used to be that folks would hand in something that they'd borrowed from the internet and just made a few changes to it, and that was their assignment. And I'm here to tell you that if you try to do that for your major project, we'll know very quickly. It's really obvious when something's come off the internet and had a few numbers changed, and it's not going to be acceptable. So make sure that you're putting in the artistic work to do sketches, to incorporate the theme properly and significantly, to make sure that you're doing the artistic work that updates things from your inspiration sources. If you're taking some inspiration from the internet, sure, take some code, but you need to do the work of incorporating it cohesively with the rest of your assignment. Basically, if you're taking an example from the internet and plopping it into your assignment, we just mark the bits of the assignment that haven't come from the internet. So it's not really doing you any benefit, if you understand what I mean. If you're thinking about putting a fractal tree in your assignment, maybe don't, I would say. Fractal trees are kind of everyone's first exercise in P5. So it's very obvious when that code has been borrowed from the internet and dropped into an assignment. It doesn't do you any benefit having fractal trees there. Another one, noise waves, the Perlin noise. Unless you've got a really good reason to use that Perlin noise and you do it artistically, maybe better just not to have it. Conceiving of the theme too narrowly. Think big, think broad, think outside the box. Folks, our themes, it's only 2 words this year, after hours. There's a lot that you could do with that. Certainly some folks are thinking about after hours in a shop or an after hours kind of aesthetic, a nighttime aesthetic, that kind of thing. Those ones are pretty common. I've seen a lot of examples of that. So you could, for folks thinking about maybe a literal interpretation of the theme like that, think a bit deeper. What other aspects of the theme, those 2 words, could you be incorporating into your work? And how could that make a deeper experience for the viewer? So there are lots of ways to conceive of these themes, not just drawing a shop that's closed. There are many ways to incorporate that concept. Think about the interactions. How are interactions tuned by that theme, not just the aesthetic, the visual aesthetic of your work? Last one, and this is an important one. Don't make a PowerPoint presentation for your major project. We've seen this before. Again, a previous year problem. We've done a lot of 1720 projects in our time, and I've seen a lot which will be like one nice scene and then another nice scene and another nice scene, and not a coherent kind of interaction between them. So the problem with a PowerPoint presentation, again, is that it's similarly to a game. It kind of has a start and an end point, whereas I'm expecting an interactive experience which will kind of evolve, allow me to jump in and get interested or jump out at any time. More like an artwork on the wall in a gallery than a presentation by someone at a lectern, like this person. So no, don't make a PowerPoint presentation. If you show the tutors something that looks like a PowerPoint presentation, they'll probably say, that looks a lot like a PowerPoint presentation, we suggest you don't do that. Okay, that was my pep talk for for the major project. We get to go to the main topic for the day, the code theory topic. What's today's topic? Today we're taking some inspiration from nature. What does that mean? We're thinking about how objects in the world move, friction, force, fields, growth, reproduction, decay, collaboration, ecosystems. All of these words are kind of natural occurrences in the world, part of the natural world, physical world, as well as the ecology of Earth, biological world. These are all things that change, dynamic systems. We want to simulate these things, and then we want to explore dynamic, that is changing, and emergent behaviors. An emergent behavior, that word emergent, is a cool one. We'll talk a bit more about that as we go through this lecture. So for this concept, I'm referring to a book that you might like to have a look at online called The Nature of Code by Dan Schiffman. This will be the textbook for, I guess, a second course in creative coding. So right now you're doing a first course, Introduction to P5, Introduction to Making Interactive Artworks, and The Nature of Code is what you might do after finishing this. Sadly, we don't have a second course for you to do, but you can certainly look at the textbook for free online. If you look on the P5JS website, there's a whole lot of examples under the title Simulate, and these generally have come from this book. By the way, this book uses a slightly different programming system called processing, not P5.js. Processing uses Java, not JavaScript, so the examples are a little bit different, but they're more or less doable in P5.js as well if you want to. First little topic in this will be vectors and physics. We've had a look at this before, how things move, how you can make them move realistically. So there's some noisy thing happening outside. I hope it's not coming through on the stream. How do things move, and can we simulate that in P5? Just going to make another editor window. Got my editor window. So in this little demo, we're going to use a vector, p5.vector, which is an object that wraps up an xy value. We've talked about this before in the objects lecture, but just to remind you, we make a vector like this, vec equals create vector 1025. It doesn't have you could use a constructor, but it's got its own kind of a function, high-level function in P5 to help make these vectors. X equals vec.x and y equals vec.y. So we can give this vector a value and then get out the x value and get out the y value. And the vector object, it gives us a lot of help in representing how objects move in 2D in processing. So let's have a look at this little skeleton. I'll go through this in detail. This is the setup. Setup. So I've got my ball. Oh, I need to let ball. This is still old code from before let. Let ball. Function setup. We're going to create a canvas and make a ball. And a ball is going to be an object with a position. Position will be 78,231 and a velocity. So it's going to have a vector velocity because it has velocity in each direction, right? The ball has a location in x and y, and then it's got a amount of movement both up and down and left, right. So the velocity is also a vector. The velocity is 2 minus 10. So it's moving to the right and moving down by minus 10. That's the velocity down. It should be up, right? Because it depends how we draw things. Anyway, then we've got a function in our object to draw this ball. So the function will simply draw a red dot on the canvas at the location of this dot pos. So remember last week we talked about how this refers to this specific object, the one we're talking about, the one that this method is inside, and that's going to be right there. So we've got this ball here. We've got another function here, update ball position, which we haven't filled in yet. So let's just draw what's happening. I might add to the draw. We've got background 220, that's fine. I'm going to add ball.drawBall to my sketch. And I should get a red ball there. So far, so good. So now, here's the trick. We're going to fill in this update ball pos function. Let's make sure this is big enough to see. Fill in this update ball pos function. Before I do, I'm just going to slightly check what's going on with my stream. Everything good? Yeah, there's a few people watching. Good on you folks for watching. Thanks for joining me today. Live. There's a couple of people around, so worth doing. Update ball pos. What is going to happen now? So the position and the velocity have to interact to update that position. So we might say this dot pos dot x plus equals this dot vel dot x. So the velocity here is going to, oops, the velocity here is going to be added to that vector. So the velocity here is measuring number of pixels per frame, I guess, not kilometers per hour or meters per second, but number of pixels per frame. So if it's moving 2 pixels per frame to the right, that means that every frame we just need to add that number to this number to update it. And we don't need to change the velocity, we're just changing the position here. And then we need to do this dot pos dot y, similarly, plus equals this dot vel dot y. Okay, so this is going to update the position. So far we're not changing anything about it, but if I add ball dot update ball pos into my code in the draw function, my ball should move. Whoo, it runs off the screen. That's exciting, isn't it? So because y counts up as we go down the screen, a negative y velocity makes the ball travel up, which is kind of counterintuitive if you think that up should be positive, but it's not in computer graphics. So minus 10 is going to make the ball move up. What next? Ball model skeleton. I've got my draw loop. That should work. Moving the ball, this is what we just did. And now a bouncing ball. So, a bouncing ball. In my update ball position, I'm going to make it so that if the ball hits one of the edges, it turns around and comes back. So if this dot pos dot x is greater than width, or do you need 2 uppy downy strokes for or? This dot pox, not pox pos, a pox on both your houses. This dot pos dot x less than 0. Then I'm going to change the velocity to be negative, it's negative value. So if you throw a ball at a wall, your velocity towards that wall, I suppose I should be pointing this way, it should bounce back this way towards me, right? So as soon as that hits the wall, its velocity is the negative of what it already was. So if it's moving away from me and its velocity is 2, when it bounces it should be minus 2 coming back. So I'm going to change this to this dot vel dot x times equals minus 1. That should do it. If this dot pos, similarly, if this dot pos dot y greater than height, or this dot pos dot y less than 0, then we're going to say this dot vel dot y times equals minus 1. Okay, I could probably do some more work to make sure that it doesn't fall off the edge of the screen, but let's just see how this goes. Bouncy, bouncy. A bouncing ball. So we're using just a little bit of a physical model of this ball bouncing in 2D to make it bounce around the screen. And isn't it lovely? The bouncing ball bouncing for eternity. We live in a world here where there is no friction, is there? Because whenever, like if you throw a ball at a wall, it doesn't come back to you with exactly the same speed as the speed at which you threw it, right? Bouncing it off the wall takes away a little bit of energy. So let's make sure we take away a little bit of energy when we bounce off the wall. We'll, instead of multiplying by 0.1, minus 1, we'll multiply by 0.95. That means it's not going to bounce forever. It'll slow down. Yeah, it's a bit stuck now, isn't it? Slowing down. And then eventually it just gets stuck. I'll turn off my wall friction because it's more fun to see it just bouncing forever. I think we're going to do gravity in a minute. What about gravity? Bouncing ball with gravity. So, gravity, moving down, gravity is a constant acceleration towards the ground. It's as if there is, when you have an object up here, you let go, its velocity is 0. But you know that the object is going to start moving towards the ground. So it starts with 0 velocity. As soon as you let it go, it starts gathering speed as it moves towards the ground. And eventually, you know, if you had dropped it from a very high height, it would move faster and faster and faster until it hits the ground. And it would only stop moving faster because like the air friction, air pressure below it is stopping it from accelerating any faster. So, I mean, you probably have done a little bit of physics and know that if you drop an object, it will start accelerating towards the ground at 9.8 meters per second. We're not going to measure meters per second because we've got pixels per frame. We'll just do a kind of approximate gravity here. But what we want to do is that every frame, we want to add a little bit of velocity in the y direction to our model. So we're going to say this dot vel dot y plus equals 0.5 every frame. So it's going to add a little bit of y velocity. This dot vel dot y plus equals 0.5. Okay? Bounce, 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 bounce. Now, instead of bouncing right up to the ceiling, it's getting pulled back down again, isn't it? Why does it slow down here? Someone tell me why the ball slows down. Shouldn't it be bouncing perfectly forever? There's no one listening, probably. Or no one listening with their pox on both my houses. Seems good to me, yep. So probably if we tune this velocity, we can make it bounce for a bit longer. That's still slowing down too much. 2. Probably still going to slow down, isn't it? It's got a nice perfect parabolic curve as it's moving around, just like a real physical model. It is a real physical model. Whoa. And then the ball kind of jumps off the screen eventually. I could probably fix this by doing something like making sure that it never goes, if I detect it across the edge of the boundary, that it gets moved back. So if this dot pos dot x greater than width, oops, then this dot pos dot x equals width minus 1. Just not let it jump off the edge of the screen. If this dot pos dot y greater than height, if this dot pos dot x less than 0, this dot pos dot x equals 1. If this dot pos dot y less than 0, this dot pos dot y equals 1. I'm losing velocity when I hit the boundary. No, I'm not. I've got that. This dot vel dot x times equals -1. Well, this doesn't work, does it? Maybe like this. Sort of getting stuck at that boundary. It's even worse than it was before. I'm sure there's some way to fix this. I'm not going to go too deep into this this argument. Why does it slow down? Well, eventually, the bounces are perfect, but the problem is that it's always losing a bit of y velocity. And probably when it goes a little bit lower than the boundary there, it never regains the velocity that it's losing on the way up. So I need to be putting back some energy into it to make up for the velocity that I lose to gravity. I need to be giving it a bounce somehow. Another push when it's going down. Yeah, anyway, this is only a short demo. I just wanted to have a look at this Charles Bounce 2022. Just wanted to have a look at this kind of physical model before moving on to some other stuff. Here's an example of the completed ball object. It's right here for you to try out and incorporate into your work if you want to. Next one, game of life. We've got 3 demos for the day. Game of life. We've simulated a ball. How about simulating an ecosystem? Well, it's quite different than a ball, isn't it? But well, let's just talk about this concept. What's the simplest way to simulate an ecosystem? Well, there's a very simple way of dealing with this, which has been used for many, many years, really. And this way was invented by a mathematician called John Conway from Princeton University. By the way, this is like academic room goals, workstation goals. Should be this number of books versus big chunky 90s computer. Classic academic look. The point of this idea is to make a very simple game that is representing a little ecosystem. So little creatures that live and die, and that's all they do. They just live and die in a little world based on some rules. So this was called a game of life. It was a little example invented by John Conway to represent how little creatures might live or die in a very simple environment. So, it's actually not a computer game. It was invented first to be done with pen and paper, which would have been very boring. But John Conway was a mathematician. He had many contributions, and he was contributing to what people would call recreational mathematics. So you'd be sitting with a pen and paper at home and kind of doing a little puzzle or something that would be just some fun with maths. I guess something like Sudoku puzzles that we do today are kind of a recreational mathematics. Game of Life is one example. You can look more about it on Wikipedia or really anywhere else. There's lots of versions. But the idea is that you have a grid of little blocks, and the blocks can either be empty, in which case they don't have a creature in them, or they can be filled in which case they've got a little creature. And the little creatures sometimes spontaneously come into existence, and sometimes spontaneously die, run out of life force. And if you set up certain little patterns with the Game of Life, you get some little cute things happening. So we'll try a few of these before. This is a famous image from Wikipedia of a few different patterns in Game of Life that continue to move. Sometimes you'll get a pattern that just dies out quickly, or it fills up the screen, or it never fills up the screen. But it's cool when you get patterns that continue to move. And this is what we call an emergent behavior, because these little guys, little movers down here and little big spaceships up here, they weren't programmed into the game. They just happen to exist within the rules of this environment. They emerge from the simple rules that we set up. So here's this concept. It's called a cellular automaton. This is the grander concept of the game of life. You've got cells here that live on a grid, and each cell has a state. It can either be true or false. Each cell has a neighborhood of adjacent cells. So this one has a neighborhood of that cell, that cell, that cell, that cell, and that cell. The cells can change state according to their neighborhood. So they can either become true, come to life, or if they are true, they can become false, in which case they die. And here's the rules of life. If a cell happens to be alive and it has more than 3 neighbors, it dies. Overpopulation rule. If a cell happens to be alive and it has less than 2 neighbors, it dies. So that's the loneliness rule. If a cell is dead but it has exactly 3 neighbors, it comes to life spontaneously. That's the birth rule. So over here, here's a cell that has 1, 2, 3, 4, 5, 6, 7 neighbors. So that's more than 3 neighbors. This cell is going to die, overpopulation. This cell over here has 1, 2, 3, 4, 5 empty spaces around it. It's actually on the edge, so we don't really count those usually, but we will in this example. That one should die because it doesn't have enough neighbors, so it's going to die of loneliness. Can I find one that's going to come to life? This cell has 1, 2, 3 neighbors, exactly 3 neighbors, so it's going to come to life spontaneously. Birth. So these are the 3 rules of life we've got. Now, we're going to do this in P5. I'll just make sure I'm back on my rules of life screen because I have to refer to it. How can I get out of full screen? There we are. Charles Life 2022. What we got here is an empty block. I'm just going to stop. What's going on with my keyboard has stopped working. Uh-oh. I hope you can hear me. I've still got some audio, which is good. Oh, it still works, cool. Keyboard's still working, that's good. Okay, don't know what was going on there. Sorry, I thought all my computer had crashed in some way. Sorry for the clicks in your headphones if you were wearing them. Cells, update cells. Get rid of that one for the moment and just show you here's my game of life. I'll make a small one to start with. I made some of this earlier because it'd be a bit too much to draw out now. I've drawn up a grid of cells. I've created a canvas. I've got a function which is going to fill my grid of cells randomly with a 2D array. And I can print them to see what's going on. Let's just go through these functions I've already got. The setup function, we set up our canvas, then we fill our array randomly. So I'm going to start with an empty array, and then I've got a number of rows, 9 rows and 9 columns. So for each of the 9 rows, I will start a new array for that row, and I will fill that row with a bunch of true or false booleans. So each row of my array, this is the 0th row, it's going to be full of booleans. And the 0th row, actually, the very last and first rows will always be all false because I don't want to use those edges. The edges get a bit weird in Game of Life. You've got to deal with them somehow, and I deal with them by making them all false. So I've got my second row, which is going to be false, false, true, true, false, 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 true, false. And here it is. False, false, true, true, false, 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 true, false. So I don't need to store any more data than just a Boolean for each of these array values. So I've got a little bit of logic here just to make sure that I fill the first row, the last row, and the first column and the last column with falses. Other than that, I just push random false or true. onto each of those arrays. And I'm using push, which we learned in about week 3, remember? Or week 4. New cells.push row, and now I've got my 2D array full of cells. The next thing we have to do is draw them. How do we draw these cells? We have to iterate over this array, and for each one of these cells we have to draw a little rectangle. So the first thing to do is to work out how big these rectangles should be. We figure out the rectangle width and the rectangle height, which is the width of our sketch divided by the number of columns, and the height of our sketch divided by the number of columns. For let I equal 0, I less than rows, I plus plus, so we're iterating over our rows. We get each row, and then we iterate over the columns, and then for each of these columns, we work out if it's supposed to be a filled-in square or an empty square. If it's filled in, if it's true, if that cell is true, we color it with dark gray, and if it's not true, if it's false, we color it with white. And then we draw a rectangle. We always draw a rectangle for each cell regardless, because when we get to the next frame, we obviously want to erase the cells underneath. Or we might want to erase them. So that's the draw cells one. Now I've got a function here that we're going to fill in now called update cells. So far it's empty. It just receives our list of cells, our 2D array C, and then we start a new array and we're going to return that. I've already filled in this function called getNeighbors. So this is going to return a count of all of the alive neighbors around my cells. So I get my 2D array of cells, and the I location is the column or the row, and the J is the column. So then I just check each case. There's 1, 2, 3, 4, 5, 6, 7, 8 cases to check. And I just check by saying if that cell, it's either going to be true or false in that cell, neighbors plus plus. Neighbors starts at 0. So it's really, really simple, just going through each option, each of the 9 locations around a cell. Okay. So what I need to do here, let next cells start like that. I think what I need to do is go over all of my rows and columns. So I'll start by drawing in a for I equals, let I equal 0. Just the same as I did up here. I less than rows, I plus plus. I less than rows, I plus plus. Okay, and then I get into my columns for let J equals 0. J less than columns, J plus plus. So right now my new 2D array of cells, I'm going to make a new array for each frame, by the way. You get into trouble if you try to update your array while you're running this program, because later cells rely on the previous cells that you're overwriting for their count. For each row, I will say let new row equal that. And then after we sort out the row, we'll push it onto next cells. Next cells dot push new row. Should be right so far. Just like I'm doing this. Actually, I'm just going to move my function up there so I can see the other one simultaneously. We want to just do this very similarly to the previous way we're doing it. So I'll copy in some data from there. Got my new row, next cells, new row, next cells dot push new row. So far so good. Now I need to, inside here, check if I am in the last column or the last row. or the first column or the first row. So if I is 0, just the same as I've got up there, that's the first row, or j is 0, or I is rows minus 1, or j is columns minus 1. That means I'm in the last row, last column, first column. If that's the case, I just will push new row dot push false. It's always false in those first rows and first columns. If I'm not there, I need to do some work to figure out what my cell should be. So the first thing I'm going to do is to get neighbors. Whoops, let neighbors equal get neighbors Cij. So it's going to count up those neighbors. I might print out my number of neighbors. At some time it might be useful to see that. Get my number of neighbors. I've counted up my neighbors all around me. And now I have to make a decision about what to do. So what is my decision going to be? There were 3 options, right? If it's alive and it has more than 3 neighbors, it dies. Okay? Oops, that's the wrong one. Child's life. If, it should be C, I, J. If it's alive and neighbors greater than 3, then it dies. New row dot push false. So this one is overpopulation. Okay, next rule. If it's alive and it has less than 2 neighbors, it dies. Loneliness. New row dot push false. Loneliness. I've forgotten what I did here. Else if C, if it's not alive, if it's dead but it has exactly 3 neighbors, it comes to life. If not C, I, J, and neighbors equals, whoops, neighbors equals 3, spontaneously comes to life. New row dot push true. Birth. Okay, and there's one more thing we have to take care of, which is if none of these things are the case, we're just going to put the current state in there. If nothing else has happened, we say new row dot push C, I, J. Okay. Nothing changes. The 4 possibilities for the rules of life. Because it could be possible that it's dead and it has no neighbors, in which case it stays dead. It could also be possible that it is alive and it has exactly 3 neighbors, which is great. It can stay alive if it has exactly 3 neighbors. It's not going to be overpopulated, but we'd still need to push it onto the new array. So this way we should get exactly the number of cells we require. The same 2D array. If we don't, then our program will crash. Let's give it a go. Hey, it seems to be working, and it's got to a static point, which is cool. So this one is not going to change. It doesn't have less than, this one doesn't have less than 2 neighbors, so it's not going to die. This one's got exactly 3 neighbors, not going to die. That one's got 2 neighbors, not going to die. They've all got 2 or 3 neighbors, so no one's going to die here. But no one has, there's no empty ones with 3 neighbors, so it can't get any, we can't have any more cells born. We'll try another one, another round. Another few static points. So this is often the case with a small game of life. You get a few little static points, or it dies. Let's try a bigger game of life and see what that looks like. 25, 25. Oh, you get some spinners. So that's a classic dynamic little system that emerges in the game of life, is ones that just spin and spin and spin. Okay, I think this one's called a boat and that one's called a rock. There's little names for all of the different things that can happen in games of life. People have gotten quite obsessed with them over the years. So this is pretty fun. We made a little ecosystem, and every time we run it, we get some different behaviors, and it's quite fun to see. I guess if we wanted to make this an interactive work, we could make it so that when the user moves their mouse around, it draws out some little little things. Oh, that's a cool one down here. Wow. I don't think I've ever seen that before. Crazy. Yeah, so the user could add some cells or add more energy into the game of life. We could make it a bit harder by making it easier for cells to die somehow, making it so that there's less options for them to stay the same. We can make it easier by allowing them to be born more easily. For example, we could make neighbors equal 2, they'll be born more easily. And then never really get to that sparser point. Yeah, so the code here is linked somewhere in the slide, so you can try this out by yourself. And if you want, incorporate it into your project. It's a really popular concept, so if you do want to incorporate this into your project, you'd have to do some work to have a take on it which works in the scheme of your major project. Just having a game of life is not going to be that exciting because it's a very old and understood example, really. But just to show you how you can make a simple ecosystem with a few simple rules and get some cool results. There's one more classic artificial life concept, which we'll just look at a little bit more briefly. This one's called boids, boids, which sort of is like a bird and like a kind of artificial computer graphics technique. What do boids do? So boids was a computer graphics program invented by someone called Craig Reynolds in the 80s. And the idea was to study how a flock of creatures could be animated to look like a flock. So if you see a big flock of birds moving through the air, they move all together in some way. How are they doing that? How are they so seamlessly seem to be able to make a collective decision about where to go? And particularly when you get a flock of really little birds, they seem to move so quickly. How do they make that decision? So Craig Reynolds was studying this and trying to represent this concept simply without using too many computational resources, because obviously we have had limited computer graphics systems in the mid 80s. And there was another kind of complexity here, was making these flocks of creatures not only move together but also avoid obstacles, so they could move away from certain things in the way that we observe creatures doing. So it's a simulation of coordinated animal motions. You can read the original paper from the mid-80s, similar to birds or fish. So we make these little generic creatures called boids, and they're just going to be represented by triangles. So you can see some here, little triangles, and here's some little triangles like we'll do today. this is super widely discussed as an example of an A-life program, showing some, similar to Game of Life, showing the emergence of complex behavior from simple rules. So just in the Game of Life, we had 3 rules. We've got 3 rules here as well. 3 simple behaviors for these voids. Separation, alignment, and cohesion. So separation means they don't want to be too close to each other. They're not going to overlap because they can't be overlapped in space. So this little flock over here, they're too closely spaced and they'll want to spread out somehow. Alignment means they're all trying to go in the same direction. So each little void is going to be seeing what their neighbors are doing and trying to make sure that they're pointing in the same direction as their neighbors. And then cohesion, they want to always be in the center of the group. So when little birds or little fish are flocking, one of the things they're trying not to do is to get eaten by bigger fish or bigger birds. So if they're on the inside of the group, they're unlikely to get eaten. So they're always trying to get on the inside. So act as a team. So they've got to be separated so they can fly or swim in space. They want to be aligned so they're all moving together, but they don't want to be too far away. So they're trying to move back into the center. So here's a void, has a direction and a velocity, and it can steer left and right by an angle. And it reacts to other voids in a small neighborhood. So here's a little image from Wikipedia showing how this works. Separation is don't crowd. So we want to adjust our steering to move us away from nearby voids. So if there's 2, these ones are close, we want to move our heading away from the 3 we've got. Alignment means that if we've got a bunch of voids around us and our heading is this way, this is our direction we're swimming or flying, we take the average of all of the other voids' directions and we push our heading a little bit to the same direction as that, the other voids. It's all about moving. We're not moving our void directly because it's just flying in a direction at a certain speed. We're just going to adjust our direction. That's the only thing we're changing here. Cohesion means that if we find a local group of other voids and we want to move towards the center of those other ones. So we've worked out the average position of voids around us and we're trying to move our heading back towards that point. So here's a little demo. I've referenced Dan Schiffman's voids. This is just an example from the P5 code. And I've copied this into a P5.js editor and made a few little changes so that we can mess around with it a little bit. Can make new voids with our mouse here. And you can see they're really fun, aren't they? They're really moving about. Let's look at our own voids. Charles voids. That's not Charles voids. There they are. We'll just run this, and there's one moving by itself. Have a few more. Let's talk about how this works. We make a canvas. We are using some object code to create an initial set of voids. I'm using a class in this case. I know Melody had me on classes last week. It's useful in this code. I guess it's inspired by Java, so classes are useful here. We'll have a flock, and it's going to have a constructor which keeps a list or keeps an array of voids around us. So each void will be an object, and the whole flock of voids will be an object as well. So when we add a void, we just adding that to our array of voids we've got, and then when we run our flock, for each void in our list, we're going to run the actions of that individual void. I don't really like this way of doing it. For b of this dot voids. This is I'm just editing my code on the go. b dot run. That's a bit nicer, isn't it? Using a for loop rather than a for loop. I don't really like for loops. Too many numbers. Okay, so the flock is relatively easy, but what about the voids? That's where things get a bit tricky. Here's a void. We get a constructor, and it's going to have a few properties. It will have a position, of course, with a vector, x, y. It will have a velocity, and they start with a random velocity, so they're moving randomly in any direction. And then an acceleration. And then we've got a few little constants we're going to use later. R, a maximum speed, because they can speed up and slow down a bit, and a maximum steering force. So this will help us kind of tune our system to look good. Because really it's a graphic system. It's important that it looks good as well as works. So we run our void by doing a few behaviors. We do its flocking behaviors. That's the 3 separate, align, and cohesion behaviors. Then we update its position, similarly to as we did with that ball earlier in today's lecture. Then we'll work out if it crosses a border. So one of the nice things about this little demonstration is that if they run across a border, they come across on the other end of the screen. So they can just pop through and just keep swimming in any direction infinitely. Then we draw it on the screen. So let's just go through these in backwards order. This dot render, that will just draw our little triangle. It knows which way it should be heading. This dot velocity dot heading, which is taking its velocity, its movement direction, and translating that into an angle, and then using that to translate a little triangle. Here's the little triangle, vertex. And R is being used as the size of the void. So if we make R bigger, our voids should increase in size. There's a big void. Too many voids. Make them smaller. Mini voids. So that's render. What about borders? This one's easy if it moves across the edge of the screen. So if this dot position dot x is less than the width of a void, minus the width of a void, it's off the edge of the screen, then we move it to the other side. This dot position dot x equals width plus this dot r. So it's not moving the void until it actually gets off the screen. If this position dot y is less than minus this dot r, and similarly, if this position dot x and y are more than width plus this dot r. A lot of similar concepts as we did with the bouncing ball here, but handled a little bit more nicely in this example. Now we've got our update function. So just like we had that update the ball function, which was going to add a bit of velocity in the y direction, we can add some velocity with an acceleration vector. So the acceleration vector is going to contain a change to the velocity in both x and y directions here. So we can add that to the velocity vector using the vector.add method, which is really handy. This is one of the reasons we use vectors, because we get these useful methods built into them. We add our acceleration to our velocity, then we limit the max speed, limit the velocity to the max speed, we add velocity to position, and then we erase the acceleration. So after each frame, the acceleration goes back to 0 for each void. And we're changing that acceleration by the separate, align, and cohesion behaviors. So here's where we do our flocking behaviors. This.acceleration.add, this.separate voids, this.acceleration.add, this.align voids, this.acceleration.add, this.cohesion voids. So 3 behaviors, they're all doing one thing, which is changing the acceleration. So it's really like someone's got a steering wheel of this void and it's just being pushed left or right by that vector. So here's the three functions. We'll look at them: separate, align, and cohesion. There's another function here called seek, which we're not going to look at right now, but we'll look at separate. This one checks for nearby voids and steers away. So I've got some desired separation as 25, just some number that you have to tune. We have make a steering vector, and then we're going to count all the voids in our system and check if they're too close or not. So we check them all, let d equals the distance between a particular void we're choosing and our current void, and then if d is greater than 0 and less than desired separation, we make a vector pointing away from that neighbor. So we keep adding little vectors pointing away from every neighbor, weighting it by the distance. So it's getting divided by the distance. So these are all of the locations of these other voids is making a vector for us to try to point away from the weight of the group. So if there's a really big group of voids near this void, it will have a very strong vector to move away from them. Here's alignment. So for every nearby void in the system, we calculate the average velocity. Work out our distance of our neighbors. We just want to look at nearby voids here. And then we will make for each void, we work out its distance. And if its distance is less than the neighbor distance, we add its velocity to our sum, and then we divide our sum by the number of voids we've counted. We multiply it by the max speed, and then we make our new steering vector. And then the cohesion should be finding nearby voids, finding their average location, and then pushing our steering vector towards that location. Now, the example here is linked in the code. You can go and play with this now. I want to keep moving with this lecture. And it's a little bit complicated to go through each of these little steering vector things in a live code situation. So I'll let you do some more work on this on your own if you're interested in how voids work and getting more into those 2D vector concepts in P5. Which is super useful if you're doing some kind of modeling exercise like this. And stop. So, why should we do any of this stuff? Why should we be simulating ecosystems? Why should we be simulating physics? Why should we be simulating flocking behaviors in P5? What's the point of this? The point is that when you're doing this kind of work in P5, you use coding to multiply your creativity. So you do the work to set up a system, make a 2D array of blocks or an array of little triangles, and you set up some rules, which obviously in Game of Life the rules can be quite simple. Once you've set up the system and the rules, you get emergent behaviors for free. So you could sit there all day and watch those little triangles move about. They're fun to watch. They're doing special things. They're behaving in funny ways. And you can tune the numbers to make them work in other funny ways. In the Game of Life, you get these little static things, little movers, little patterns that occur and disappear. These are all behaviors that emerge, a complex phenomenon emerging from a simple system. So you get these for free. And the point of this slide is that you can do this in P5. You can't do this in Photoshop, Final Cut Pro, Premiere, or Ableton Live. So even though you can do some amazing artworks in Photoshop, you can't make a generative system because there's no way to make the rules. You don't get to make the rules. Photoshop has the rules for you. and its rules don't change over time. You can apply complicated filters that do complicated things, but they're only doing the one thing that the programmer of Photoshop set up for you. When you're making art in P5, you get to change the rules of how it works because you're the coder, which is pretty special. It's one of the special things about art and interaction computing rather than just media artworks that you can make with computer software. So take advantage of that special thing. Don't make things that are static systems. Don't make things that are boring. Make things that have rules and behaviors that emerge and that don't work the same way every time. Because that means you're really using the affordances of P5 rather than relying on the drawing tools that it's given you, just like you might do in Photoshop. One way of thinking about this kind of computing is that we might be doing something like making a computer behave in a creative way without our intervention. So there's a concept called computational creativity, or a field. And this field is all about different ways that we can work with computers to make them behave ways that when we look at it, we say, wow, isn't that creative? And it's this field has been taken over a little bit by like AI generative artworks recently. We talk more about that next week. But it's been happening for a couple of decades before that, including things like Game of Life, cellular automata, Boyd's, flocking. All of these concepts are built into this field of creative computers, computational creativity, creative computer programs, and artificial life. And there's a famous theorist called Margaret Bowden, creativity theorist, who's written about how computers can express creativity. Not in the same way that humans express creativity, but thinking about what it is about creativity that is really important and makes it feel like a creative system. So three topics. One topic is novelty or newness. So it feels like the system should be creating things that are new. Another aspect is utility or value. So not only should there be things that are new, but we should like them in some way, or they should have some value. I guess value is a more abstract way of saying that it's qualitatively good. In an artwork, you could say that it's got sort of aesthetic value. But you might say that that's subjective, and there are other ways for artworks to have value. They could have political value, or be commenting on society in some way, or technical value. So there's lots of different values that you can have about an artwork. We've already discussed that at length. But obviously, for something to be creative, it should have some kind of value by some other lower level descriptor. Novelty, value, and then the third one, and the tricky one is surprise. Novelty, value, and surprise. So I was surprised today when we finished off the Game of Life, when it made a little thing that I'd never really seen before in the 25 by 25 one. I'd never seen that particular little pattern. It was really a cool one, and I was a bit surprised. So there you go, a cool creative system. It had novelty, it had some value, and it had a little bit of surprise. So the funny thing about A-Life, artificial life art, is that it's full of surprises. These systems usually have pretty simple rules, and we feel like they shouldn't be as compelling that they are, but they just are compelling. They always have these concepts of novelty, utility, and surprise that make them feel like worthy works of art to look at. So I've got a few little examples of artificial life in art. By the way, this image, this background, it's a photo of an artwork. I've forgotten what it was called now. But I took this photo at a conference called the Conference on Artificial Life, and they had an art gallery as part of that conference. And this cool artwork had these little fronds that would move a little bit and light up in a different way. So it was a simple concept, a little board here that was controlling this little individual light and little moving. It would only sort of wave a little bit, I think, not moving very much. One simple thing, then you make a lot of them and you get this little ecosystem. So it's easier to do this stuff in code than to have to manufacture little boards, but still it was a this high-level concept of taking a simple thing and then making a lot of them that can interact together, and then it becomes something that seems creative. It seems like it's got novelty, utility, and value. Novelty, utility, and surprise. Let's look at some other ones. This artwork was called Sound for Fungi by Therese Schubert. So the concept here was modeling in some way the way that a fungus grows. So the artist had studied how funguses grow and recorded data about growth, and then was representing them within a 3D rendered artwork with sound as well. And then there was a little sensor down here. It's one of these sensors. This is called a leap motion sensor, which is a movement sensor for your hands, or a distance camera. And they were using that camera to sense where a viewer had moved their hands around the artwork and would change the model of growth in this modeled fungus and the sound that goes with it as they move their hands around. Therese Schubert has a lot of these works. It has done them in different ways. This one's in a sort of screen on a wall kind of technique. And then there's other examples like Always Dead and Alive, which has another kind of generative artificial life form projected on a huge screen with people sitting down there, again with sound and vision. This other one, Heliotropica. I've forgotten about Heliotropica. What was the concept with this one? Juan Manuel Castro. Definitely a cool concept. So this one was, Heliotropica creates an interface between people and cyanobacteria mediated by light. The product integrates the photosynthetic activity of cyanobacteria, the dynamics of environmental life, and the bioelectrical activity of the participants. Using microscopic observation, cell culture, and computer vision, this work renders the photosynthetic activity of cyanobacteria in the form of an organic structure, produces dynamic geometries of light by analyzing environmental data. So I think in this one, they had to have the actual bacteria. The previous examples were models. This one had actual bacteria in some culture somewhere, and then a microscope looking at it, and then the bacteria culture would be displayed on the screen. There'd be some kind of visualization of it and some light played back. And there would be some kind of interaction between what participants were doing, sensed by some other thing, some other camera, I think, viewing the participants. They would be sensed, and then some data would get sent to stimulate the bacteria growth using light, and then that would be analyzed to create the artwork as well. So creating a feedback network, some kind of sensing system here, a feedback interaction between an actual life form and the computer artwork and the sound in one piece. There's the culture. Here's this thing that analyzes it with some computer vision, which is pretty neat. And some different examples. So a cool artwork overall. Another concept, I guess is a heuristic, an algorithm for generating things, bio-inspired algorithm, kind of in competition with the typical machine learning algorithms we have now. This idea of an ant colony algorithm is inspired by the ways that ants move around a landscape. So if you ever watch an ant's nest, the ants move in little lines. So they're not just moving randomly. Once an ant has discovered a food source, it leaves some little smells along the ground, and the other ants like to follow that. So ants, when they're moving around the world, they're following each other and organizing themselves to follow the successful paths. So you can use ant colony algorithms to optimize a computer program in a machine learning kind of way, or to create an artwork. And these are some examples of ant colony inspired live visual artworks where different artists have used ant colony optimization to create a little algorithm, a little ecosystem of fake ants to wander around a canvas, and where they wander, it draws pixels and creates a lovely artwork. So obviously We don't know the precise rules of each of these artworks, but you can see different complex ideas, abstract works, a representative work, different ideas related to how we can apply this A-life concept into art. And that's my Creativity in A-life lecture. Folks, there's some links here for you to watch and read if you want to. It's only week 11. There's still 2 weeks left in your major project development time. Don't miss the labs you have to do this week. The labs this week and next week are really important time for you to work with your colleagues, show other people your major project, and get really important feedback from your tutors. So make sure you start your major project, go to your lab, do the lab exercises, talk with your friends in those labs, and make sure that your project is a long process of making, not a short, stressful one. So with that, I might go. I'm always available on the forum for questions and thoughts. Thanks for a great day. Whoops, where's my thing? I'm not very smooth these days with my thing. And see you next week.